There's a planet very far away but absolutely real, where the sun sets twice. Two stars sink toward the horizon, one bright and golden, the other a small, sullen ember of red, and they cast two shadows behind everything that stands in their light. For decades, this was the single most famous shot in science fiction, a lonely figure on a desert dune watching two suns go down. And then, in 2011, a telescope found the real thing, not a painting, not a special effect, a genuine world circling two stars at once, 200 light years from where you're sitting right now. Let's go. To understand why this discovery stunned even the scientists who made it, you have to understand why almost nobody believed a planet like this could exist. For most of modern astronomy, the idea of a stable world orbiting two suns was treated as a fantasy. And not because it looked good on a movie poster. It was because the math seemed to forbid it. And to be clear, these double stars aren't some bizarre exception. They're a completely natural outcome of how stars are born. Stars don't form one at a time in tidy isolation. They condense out of vast, collapsing clouds of gas and dust, and those clouds are turbulent, lumpy things. A single cloud can fracture as it collapses, breaking into two or more dense cores that each ignite into a star, born together, bound to each other by gravity from the very first moment. Two suns circling each other isn't a cosmic oddity. It's one of the most ordinary things a galaxy does. The strange part, the part we got wrong, was assuming planets couldn't join the party. Think about what a planet actually needs to survive. It needs a calm, steady path through space, the same loop year after year for billions of years. Around a single star like our sun, that's easy. There's one center of gravity, one anchor, and a planet just falls around it in a clean ellipse, endlessly. But now add a second star. Suddenly, there are two enormous masses, both pulling, both moving, both yanking on anything that tries to orbit them. The gravity isn't a steady anchor anymore. It's a tug of war that never ends. And in that tug of war, a young planet is in terrible danger. Run the simulations, and most worlds born around a pair of stars meet one of two fates. Either the shifting gravity flings them out of the system entirely, hurling them into the cold dark between the stars to wander forever, or it does the opposite and drags them inward until they spiral into one of their own suns and are swallowed whole, eaten, or exiled. Those were supposed to be the only options. So for a long time, the smart money said circumbinary planets, the technical name for a world orbiting two stars, either couldn't form or couldn't last. They were a curiosity for theorists and a playground for filmmakers, nothing more. But here's the thing about the universe. It has a habit of doing the thing you just proved was impossible. The breakthrough came from a NASA spacecraft called Kepler, a telescope with one beautifully simple job. It stared, without blinking, at a single patch of sky containing more than 150,000 stars, and it watched their brightness, looking for the faintest flicker. Because when a planet passes in front of its star, from our point of view, it blocks a tiny sliver of that star's light. The star dims, just slightly, just for a few hours, and then brightens again. That little dip is a shadow. It's the silhouette of an entire world crossing the face of its sun, measured from 200 light years away. For planets around single stars, this method is almost clockwork. The dip comes at regular intervals, every orbit, like the ticking of a precise and patient clock. You see it once, you predict the next one, and it shows up exactly when you said it would. That regularity is how astronomers confirm a planet is really there. But in 2011, a SETI scientist named Lawrence Doyle, a former protege of Carl Sagan, was staring at the light from one particular system, and the clock made no sense. There were dips, but they refused to keep time. They came early, they came late. They were deep one time and shallow the next. They changed duration, lasting longer on one pass and shorter on another. By every normal rule, this was a mess. The kind of messy signal you'd usually throw out as noise or a glitch, except it wasn't noise. It was a clue, And the reason the timing was so chaotic is the single most beautiful idea in this whole story. The planet's shadow wasn't arriving at random. It was arriving late or early because the thing it was orbiting would not hold still. The two stars were swinging around each other, and as they did, they dragged the planet's whole orbital path back and forth with them. Sometimes the planet had a little extra distance to cover before it reached the front, sometimes a little less. The chaos in the data wasn't a failure. It was the fingerprint of two suns, written in shifting light. When Doyle and his team finally untangled it, what they had was historic. The first direct, unambiguous proof of a planet orbiting two stars. They gave it a formal name, Kepler 16b, the kind of designation only an astronomer could love. But informally, almost immediately, they reached for the only name that fit. They called it Tatooine, after the desert world with the double sunset, and they even thought about asking George Lucas for permission. Science fiction had become science fact, and the people who made the discovery knew exactly which movie they were living inside. So what is this place, really? Strip away the romance and look at the world itself. And the first surprise is that you could never actually stand on it to watch that double sunset. Kepler 16b is not a desert planet at all. It's a giant ball of gas and ice, roughly the size and mass of Saturn, with no solid surface to plant your feet on. The iconic image, a person on a dune gazing at two suns, could never happen there. The planet is a frozen gas giant, and standing on it would be like trying to stand on a cloud the size of a ringed world. And it is cold, bitterly, deeply cold. Because here's the second twist. Its two suns are not two blazing copies of our own. One of them, the larger star, is an orange dwarf, smaller and cooler than the sun, and the other is a red dwarf, a feeble little star with barely a fifth of the sun's mass. Together, even combined, they don't put out nearly enough warmth at the planet's distance. Kepler 16b orbits in deep chill, far below freezing, a dim and frosty world lit by a bright star and its dull red companion. The real Tatooine is less a scorching desert and more an icebox with a view. But oh, what a view! Because while you couldn't stand on the planet, the mechanics of its sky are real, and they are stranger than anything a movie dared to show. The two stars don't just hang side by side like the painting. They orbit each other, the whole pair completing a lap every 41 days, locked in a tight embrace closer to each other than Mercury is to our sun. So from anywhere in that system, the two suns are in constant motion relative to one another. They draw together and pull apart. They rise close and set far. Some days they'd cross the sky almost as one, and other days they'd be separated. Two different suns running on two different schedules, painting the landscape in shifting double light and double shadow that never repeats exactly the same way twice. The planet itself takes 229 days to circle this dancing pair on a nearly perfect circle of an orbit. And that orbit hides another secret, one that made the discovery even more shocking to the experts. Kepler 16b sits closer to its two stars than the theories said any planet could survive. It formed and persisted inside the very danger zone where the gravitational tug-of-war was supposed to destroy it. It's a planet living comfortably in the one place it was forbidden to be, which told astronomers something humbling. Their models of how these systems work were incomplete. Nature had found a loophole they hadn't. So how does a planet survive in a place the gravity should tear it apart? The answer turns out to be distance and rhythm. Stay too close to the warring stars, and the tug-of-war does indeed destroy you. But move out past a certain critical radius, and something changes. From far enough away, the two stars start to blur together gravitationally. The planet stops feeling them as two separate bullies yanking it in different directions, and begins to feel them almost as a single combined mass, one steadier pull. There's a forbidden inner region, a no-go zone close to the stars where no stable orbit can last. But just beyond its edge, worlds can settle into paths that hold for billions of years. Kepler 16b threads this needle, sitting just outside the chaos, close enough to be remarkable, far enough to be safe. It's not defying the gravity. It found the one lane where the gravity lets it live. And once they knew what to look for, the floodgates opened. Because here's the part the headlines in 2011 couldn't yet tell you. Kepler 16b was not a freak. It was the first of a family. Within a few years, the same telescope found more of them. World after world threaded around pairs of stars. And then came the one that changes the entire emotional weight of the story. In 2016, astronomers announced a planet called Kepler 1647b. It orbits two stars much more like our own sun, two genuine solar mass stars. It's a gas giant about the size of Jupiter, the largest of these double sun worlds found at the time. It takes a staggering 1,100 days, just over 3 years, to complete a single orbit. But the number that matters most isn't its size or its year, it's where it sits. Kepler 1647b orbits squarely inside the habitable zone, the narrow band of distance where a world is the right temperature for liquid water to exist on its surface. Now, Kepler 1647b itself is a gas giant, so it's not going to grow forests. But hold that thought, because here's where it gets interesting. Big gas giants tend to have moons. Our own Jupiter and Saturn have dozens, and a large rocky moon orbiting a gas giant that sits in the habitable zone of two suns would be a solid world with a real surface, bathed in the light of two stars, at a temperature where water could pool and rivers could run. In other words, the actual Tatooine, the one you could stand on, might not be a planet at all. It might be a moon somewhere out there, waiting. And the discoveries kept coming, each one chipping away at the old assumption that two-sun worlds were rare accidents. A space telescope called TESS, Kepler's successor, found its own circumbinary planet, a world about 7 times the size of Earth orbiting two stars 1,300 light-years away. Then, even more impressively, astronomers found a second planet in that same system, which meant something remarkable, that two suns can host not just one planet, but an entire family of them. A whole miniature solar system wheeling around a double heart. In fact, one of these double sun systems turned out to be downright crowded. Astronomers found a pair of stars circled by not one, not two, but 3 confirmed planets. An entire layered system of worlds orbiting two suns at once. One of those planets sits in the habitable zone too. It was the proof that a binary star isn't just capable of holding a single lucky world on a knife's edge, but can build and keep a whole organized planetary system, structured and stable, exactly the way our single sun built ours. The thing the math once forbade, the universe does in bulk. This is the quiet revolution hiding inside a Star Wars reference. Astronomers now believe these systems are not rare at all. Roughly half the stars in our galaxy are not single like our sun, but come in pairs or even larger groups. Half, which means that for a long time, in our search for other worlds, we were only seriously looking at one half of the sky's real estate, quietly assuming the other half was barren. The discovery of these planets tore that assumption up. The galaxy is full of double stars, and we now know those double stars can and do hold worlds. And the hunt got cleverer. The shadow method only works if a planet happens to pass directly between us and its stars, a lucky alignment that misses most worlds entirely. So astronomers developed a second technique, one that doesn't need the planet to cross in front of anything. Instead, they measure the gravitational wobble. A planet, even a small one, tugs on its stars as it orbits, making them rock ever so slightly toward us and away from us. That tiny rhythmic shift shows up in the color of the starlight, stretched and compressed like the pitch of a passing siren. Using this, a dedicated survey began finding circumbinary planets that never transit at all, invisible to the old method, detectable only by the gentle pull they exert. It meant the worlds we'd found so far were just the ones that happened to cast a shadow our way. The rest, the hidden majority, were finally coming into reach. There's an even wilder example that stretches the imagination further. The very largest known planet of this kind doesn't orbit two ordinary stars at all. It orbits a pair that includes a dead star, the collapsed corpse of a sun, paired with another stellar remnant way out in an ancient globular cluster, a planet older than almost anything, circling the ghosts of two stars that died long ago. The two suns image turns out to have variations the filmmakers never dreamed of, from icy giants around living stars to lonely worlds orbiting the embers of suns that burned out before the dinosaurs. And the weather on such a world would be like nothing on Earth. Here, our seasons come from a simple, steady source, the tilt of our planet as it circles one unchanging sun. But on a world lit by two stars that are forever closing in and drawing apart, the amount of light and heat reaching the surface wouldn't hold steady at all. As the two suns aligned, their combined glare would pour down together. As they separated, the warmth would spread out and shift. On top of the planet's own yearly orbit, you'd get a second, faster rhythm of brightening and dimming driven purely by the stars' 40-day dance around each other. Two overlapping cycles, one slow and one quick, would braid together into a climate that pulsed in ways no earthly calendar could ever capture. Summers and winters would arrive not in a simple line, but in a shifting, layered beat. So picture, one more time, what the sky would actually look like from a solid moon orbiting one of these worlds. Two suns, but never quite the same way twice. On one day, they rise together, almost touching, and the world has a single strange dawn twice as wide as ours. Weeks later, they've separated, and now there are two sunrises and two sunsets, the second sun trailing the first across the sky like a smaller, redder echo. Shadows double and cross. The color of the light shifts as the brighter star and the dimmer one change places. A clock on that world would be a nightmare to keep, because the very meaning of a day would slide and stretch depending on where the two suns happen to be in their endless dance. And every part of that sky is real, not concept art, not a matte painting. Light from real stars falling on real worlds 245 light-years away in the constellation Cygnus, the Swan, where Kepler-16 has been quietly performing its double sunset for billions of years, with no one there to watch it, until us. Until a telescope noticed a shadow arriving at the wrong time, and a scientist trusted the mess in his data, and the impossible turned out to be just another thing the universe had been doing all along. Which leaves one last question hanging in the dark. We found these worlds by accident, the moment we built an eye patient enough to see them. So if half the galaxy's stars come in pairs, and we've already found planets and possible moons circling them in just a few short years of looking, then somewhere out there, on a world we haven't found yet, something may be standing on a solid shore right now, watching its own two suns go down. And the only thing we don't know is whether anything is standing there to watch back.